on. Okay, there we go. Indicators transition between colors when the acid form and the base form have similar concentrations. So it will be transitioning from the acid form, which is yellow, for example, and the base form, which is blue, for example. What color will Brom Cresol green be when it is transitioning between its acid form and its base form? It will be green. Yay. Brom Cresol green, although some of them are called blue, even though like that's only one. I don't know. Sometimes you'd think it was more sensible than it is. Because bromthymol blue also has a transition color of green. So, I don't know. And the reason for this is if that the concentration of yellow is approximately equal to the concentration of blue, of course, you are going to get a mixture of the two, which is green. Not necessarily neutral. These transitions take place at different pHs. Some of them transition at pH 7, some of them transition at pH 11. So it really depends on the substance. Yeah. When the acid form is exactly equal to the base form, the concentrations, we actually call that the transition point, which I am going to abbreviate TP. TP stands for transition point. It does not stand for toilet paper. Okay? Transition point. So it is the point when color A concentration is equal to color B concentration. And we can do something really nice with this because it is an equilibrium. We can always write, it's an equilibrium for a weak acid. We can write a Ka. Yes? Ka. So we have HIND in equilibrium with H plus and IND minus. And we can write our Ka expression, H plus times IND minus over HIND. At the transition point, though, remember these two are equal. And if they are equal, what can we do with them? Cancel them out. And so guess what we're left with? Ka is equal to the hydrogen ion concentration. So that means that at the transition point, when it is transitioning, your hydrogen ion is equal to the Ka. And you can also then take the negative log of that entire thing. Which then gives you what is the negative log of Ka? pKa. And what is the negative log of H plus? pH. So at the transition point, Ka is equal to H plus and pKa is equal to pH, which is a very nice relationship to know, okay? So this equality allows us to do a couple of things. If you are given the Ka of the indicator, you can find the pH at the transition point, okay? Simple math. You take your Ka and you say, oh, I know that Ka is equal to hydrogen at the transition point, and therefore I can calculate pH at transition point. Simple, straightforward calculation, okay? If you are given the pH at the transition point, if you're starting from pH, you can convert that into hydrogen, and from there you know the Ka of the indicator, okay? So let's check out page 7 of your data booklet, which lists the indicator the pH range at which the color change occurs, and the color change as the pH increases. Page 7. Does anyone need a data booklet? If you need a data booklet, come grab one. They're right here. No worries. Did you have your capstone today? Oh no! But I was gonna say, you look very professional. None of my people have really dressed like professional for me. They've dressed nicely, but they're like wearing sneakers. And I'm like, really? Really? What did you guys think of the capstone once all was said and done? It was fine? Yeah. My two students said they actually found it kind of useful in the end. Did you guys find it kind of useful? No, because you all knew what you were doing anyway, right? Yeah, okay. All right. Or you're still as lost as you were before, so. All right, so here we go. What is the pH at the transition point for methyl violet? So if you look on there, methyl violet will be listed. It changes color when the pH goes from 0.0 to 1.6. And it changes from yellow to blue. So if we look on a pH scale, when we are below pH 0, it's going to be yellow. When we are above pH 1.6, it's going to be blue. And when we are between 0 and 1.6, it is going to be green. Now, there will be different shades of green in here. I don't want you getting worried about them. Don't be like, it's a bluey green, it's a yellowy green, it's a lime green. No, 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 it's just either yellow or it's green or it's blue. I am never going to give you something like, what is the color at pH 0? And you're gonna be like, oh my God, is it green or is it yellow? I'm not gonna do that to you. Yes, that just sounds ridiculous. Okay, so don't worry about it. You're either going to be below 0 or above 0 or below 1.6 or above 1.6. It's not going to be like those little, I would say gray areas, but I guess I mean lime green areas. So low pH means you have a high hydrogen ion concentration, which means that HMV is the predominant form. The more H you have, the more protonated it will be. A higher pH means you have less hydrogen, and so MV minus, actually should have done that in blue, shouldn't I? Come here, where's my eraser? We have a lower H, which means that MV minus is the predominant form. Now the pH at the transition point is the halfway point between 0 and 1.6. So what is that value there? What is halfway between 0 and 1.6? 0.8, yes? This one's really easy because it's between 0 and 1.6, but generally you can just take the average. Yes, just add the two endpoints and divide by 2. Once we know that, once we know the pH at the transition point, we can then say, what is the Ka of methyl violet? Well, we know that Ka is equal to H plus at the transition point. Remember that, you know, that's just in brackets there if you've forgotten from 30 seconds ago that we said that, you know, you can cancel those out, right? Now, we know that the pH at the transition point is 0.8. You can find hydrogen by taking 10 to the negative pH. Yes? That will come in handy for the take-home quiz you're doing over the weekend. Yes? It's a practice take-home quiz, right? Like, if you choose not to do it, that's fine, but you might want to, because on Monday I can take a quick look at it for you and let you know if you're missing anything or whatever. Yes? Okay. Hydrogen at the transition point, 10 to the negative 0.8 gives us 0.2 molar. So that means that I know the Ka because the Ka is equal to the hydrogen at the transition point. How easy was that? Easy? Yeah, hopefully. Or you could do it the other way. You could say pH is equal to pKa. pH at the transition point is equal to pKa. And then you could say Ka is equal to 10 to the negative pKa. Yes, either way, you're doing the same math. Yeah? You guys want to try the next one on your own? Call me over if you get stuck. Did I do it right? Yeah? How many sig figs should we have in our answer? First of all, are we all okay with A and B, or do we have any questions about that? You can show your work either way. How many sig figs? Should I give my answer as 5.0 times 10 to the negative 8, or should I give it as 5 times 10 to the negative 8? How many sig figs in that pH? 1, right? Because it's after the decimal. Okay, and that means that our answer will be 5 times 10 to the negative 8, not 5.0 times 10 to the negative 8. Okay? All right. The Ka of an unknown indicator is 3.2 times 10 to the minus 5. The acid form of this indicator is red. The base form of the indicator is blue. What is the color of the indicator at the transition point? Purple. You guys are doing really well. Every once in a while, I get someone whose kindergarten teacher did not do a very good job, and they just do not know their color combinations. It's like, what was your kindergarten teacher teaching you anyway? Probably some math or something like that. I don't know. But anyway, yeah, they're like, I don't know. One year I had a boy discover that he had color blindness because I started drawing colors, and like he's like, those look the same. Yes, they do, because you're colorblind. I don't know, because you feel like, you know, when someone's like, this is green and this is red and they look the same to you, you're like, why are they giving those things different names? Anyway, I don't know. But I guess it's kind of like, you know, pink and red kind of are in the same color family, and maybe they just thought it was like, I don't know. I just don't know. I think it was red-green colorblind. Yeah, so again, maybe their kindergarten teacher wasn't doing much. Plus, don't your parents usually take you to the eye doctor and like have that checked out at some point? No? I guess unless you've got like actual eye problems, you may not. Yeah, I've always had my son go with me because it was covered under our plan. So I was like, just come with me, get your eyes checked. He's got perfect vision. I call him my little eagle eye because he can see everything. He can see everything up close. He can see everything far away. I just get him to read everything for me now. All right, at what pH does the indicator change color? Do you know how to do that? Would you like to try it on your own? Try it, go. What am I doing? No, it doesn't make any sense. Oh my God. Yeah, that's not good. Did we get the same number? Okay, what should the sig figs be? Okay, so is it going to be, oh yeah, sorry, I actually shouldn't have written that as a 5. I should have written that as a 4/8. Yes, because that'll change our rounding, right? So that would then be 4.49. That gives us 2 sig figs to match with our 2 sig figs there. What color is the indicator in 1.0 times 10 to the negative 6 molar hydrochloric acid? One really quick way to do this is you just compare the pH of the hydrochloric acid solution to the pH at the transition point. So the pH of the hydrochloric acid solution, it's a strong acid, so you just use stoichiometry and say it's 1 to 1. We end up with 1 times 10 to the minus 6. And so the pH of the HCl solution is 6. We had previously determined that the pH at the transition point was 4.49, yes? And we know that above that, you're going to have the base form, yes? And below that, you're going to have the acid form of the indicator. And we were told that the acid form was red and the base form was blue. So our acid form is red, our base form is blue, and we are at pH 6. So at pH 6, the indicator will be blue. Because who is the predominant form? HIND or IND minus? IND minus, yes. Are we good? Okay. One last note, as we go down the acid-base indicator chart, what happens to the pH at the transition point? It gets higher, so it increases. So that means that the pKa does what? It increases, which means that the Ka value is doing what? Let's think about this. It works like pH. As pH goes up, what happens to concentration of hydrogen? It decreases, right? So that means that as pKa goes up, what happens to the Ka? Ka goes down. Okay, so because we have our pH is increasing, our pKa is increasing, that means our Ka value is decreasing. So who is the strongest acid on that chart? Is it methyl violet or is it indigo carmine? Tell your partner what you think. Who is the strongest acid on that chart? What do you guys think? Methyl violet or indigo carmine? Methyl violet, yes, methyl violet is the strongest. Indigo carmine is the weakest. You can actually go through and calculate the value. The pKa is 0.8, and so therefore the Ka is 0.15. Did I do that right? No, I did not. Did I? No. 0.8, 0.158. Did I do it right? I feel like I didn't. (1.6 times 10 to the negative 1). It looks better when I write it like that. Okay. How did I go from here to here? Yes. It is a weak acid conjugate base system. Yes, so all of them are a mixture of their acid and base forms. So when we talk about the acid form, methyl violet is the strongest acid. Its base form will be the weakest base. Yes? Yes. So what is the pKa of indigo carmine? What's the pKa of indigo carmine? 12.2. That's the average of 11.4 plus 13.0. And that's our pH at the transition point, which is equal to 2, which is our pKa. And then our Ka would be 6.3 times 10 to the negative 13. Although, is that a correct answer? No, what's wrong with it? Should be 1 sig fig. Yeah, 6 times 10 to the negative 13. Is good? What? Oh yeah, this should just be 2 times 10 to the minus 1. You're absolutely correct. Yeah. Okie dokie. Oh, and then there's some exercises. So we're going to skip those. We'll let you do those later. And we're going to go along to page 10. Using acid-base indicators. So you can use 2 or more indicators to find the pH range of a solution. So if you have a solution that turns phenolphthalein pink and it turns indigo carmine to blue, what is the possible pH range of the system? Of the solution, rather. Well, if we know that phenolphthalein is pink, what do we know about the pH? We know that the pH has to be greater than 10. Yes? We also know that indigo carmine is blue. And what does that mean for our pH? It has to be less than 11.4. And so if we had to give a range then, the pH is greater than 10 and less than 11.4. We can write that range one of 2 ways. We can either put pH in the middle and say pH is greater than 10 and less than 11.4, or we can say the pH is equal to 10.0 to 11.4. That's not subtracting, that's a 2. Maybe that would be a better way of writing it. 10.0 to 11.4, that way it doesn't look like a subtraction. Okay. Does it matter that one of these ways of expressing the range includes the 10.0 and the 11.4, and one says that it's greater than 10.0 and less than 11.4? No, it doesn't really matter, because it's really hard to say when phenolphthalein, for example, stops being really, really pale pink and starts to become like really pink, right? When does it stop being really pale pink and start being colorless? Like, it's really hard, like visually it's hard to tell. So we're not gonna get too wound up as long as you've got those numbers at the endpoints of that range, okay? So I will never ask you what color is indigo carmine at pH 13, because that's one of those end range things. Would you answer green? Would you answer yellow? Probably a very yellowy green, who knows? Okay, ambiguous, let's not go there. When you are asked to find the color of an indicator in a solution, you will need to find the pH. So if we say, what color will bromcresol green be in hydrogen ion concentration? Well, you would have to find your pH by taking the negative log of hydrogen, and you look at that and you say, oh, look, 10.72 would be over in the blue region. Yes? If I give you a POH, what would you have to do? You would have to find the pH, so you would say pH is equal to, do you guys remember this formula? This is on your test next week, yes? pH is equal to pKw minus POH, so we have 14.0 minus 7.8, we get 6.2. What color will it be? Blue, excellent. And then if I just give you like pH 4, if it's anywhere in the middle, just say green. Yes? No? Okay. If you are given the concentration of an acid, you're going to have to decide, is that acid strong or weak? Because if it is strong, hydrogen is just equal to acid. Yes? But what if it's weak? What if you have a weak acid? Ka. You have to use rice and Ka. Yes? Oh, did I include it in here? I did. Remember the little old lady? She's weak. She comes along carrying a bag of rice. She drops the rice and along comes the Ka. This is actually where I came up with it the first time, which is why it is still in here again. But, you know, there we go. Okay, so going back though, if we say sulfuric acid, what do you know about sulfuric acid? Sulfuric acid is strong. And remember, in a diprotic acid, which dissociation matters? Only the first one. So 0.25 gives us 0.25, it's 1 to 1. Take the negative log of that and you get 1.60, which means that bromcresol green is yellow. Yes? What color is chlorophenol red in 0.50 molar solution of HCN? Well, HCN is a weak acid. When I give you this initial concentration, remember that's always the acid concentration is always the initial concentration, the one that's given in the question. So we'll plug that into our rice table. What are the initial concentrations of the hydrogen ion and the conjugate base always? 0. Okay, those are always 0. Where are you going to get your Ka value from? You'll get it from the data booklets. If you were to keep the X here, what would you end up with? if you had the 0.50 minus x, you would end up with a quadratic equation, and nobody wants that. Well, maybe some people do. Their calculator will do it for them. That's fine. If you want to, you can do that. Or you can make sure that you write assume x is insignificant, point at the x, write your Ka expression products over reactants, plug in your values, solve for x, la 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 la. Now you have hydrogen. You want pH, take the negative log of the hydrogen. And then finally, you'll go and say, what color is chlorophenol at 5.31? That would be in there, so it would be what color? Orange, because it's in the middle of those. Yes? When given the concentration of a base, you must also determine if it is strong or weak. Remember, all metal hydroxides are strong bases. I'm going to put a big star beside that because people tend to forget it. I don't know why. Because in grade 11, when I say base, you're like, hydroxide. Yeah, but then we get into this stuff and we kind of forget. And they dissociate in whatever ratio they dissociate in, 1 to 1, 1 to 2, et cetera, et cetera, et cetera. You can find the coefficients from the coefficients. So, is this one worked here? You know what, cover that up and calculate for me, please. So take a piece of paper, or you can just look up here and close your book for a minute. What color is thymol phthalate in 0.0030 molar barium hydroxide? Try it without looking at the answer. So what color is thymol phthalate? First thing you need to do is you need to make sure that you know that barium hydroxide produces 2 hydroxides. So what is the concentration of the hydroxide ion? 0.006. And if we know hydroxide, where do we go from there? What are 2 routes we can go from hydroxide? Okay, when they're done, we're going to do the same thing. Are you ready? We're going to do it. So we're going to do it louder than them. Are you good? Are you up with this? Okay. 3, 2, 1, go. Woo! 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 Okay, that was fun. Interactive teaching. Cross-curricular. Oh my God, awesome. Okay. So once we know hydroxide, what are the 2 routes we can go? We can take concentration of hydroxide. What can we find next? We can find the POH, and then we can find the pH. What do we use to go from OH to POH? Negative log. What do we use to go from POH to pH? KW, pKw. Okay. What does pKw equal to? Yeah. What does pKw equal? pH plus POH. Just making sure we all remember those. Now, what is the other route that you could go? You could go from hydroxide to what else can you convert hydroxide into? You can convert it into POH, or you can convert it into yes? What's the relationship there? How do we convert from hydroxide to hydrogen? What do we use? Kw. And what is Kw equal to? Yeah, it's equal to 1.0 times 10 to the negative 14, but what is it equal to as in terms of formula? H plus times OH minus, yes. See how we're reviewing for our unit 4 test as we're working through this one? Yeah, because 5 and 4 are really one unit. It's just, it's too big to put all on one test. Unless you want to just have one test. Do you guys want to have just one test? I don't know. Unit 4 is easier than Unit 5. So it's kind of nice to have a test all on its own. But think about it. All right, so now we have, so you can either do it, this shows the first way where you've got hydrogen is equal to, yes? Probably. Something to think about. We can decide, we can think about it and decide by tomorrow if you want to skip the Unit 4 test and just smush Unit 4 and 5 together into one test. Okay? Huh? This is a hard unit, but I don't think it's going to be as hard for you guys than it is for normal brains because you guys have big brains. Yes? You do, you got big brains. No, trust me. Because when I teach regular chemistry, I spend a lot of time on that sig portion of the pH and pH, like a lot of time. Like we do it like, 3-4 classes in a row and they're still like, I don't get it, right? And, then I'm like, and how do you calculate H from OH? And they're like, I don't know. Right? And maybe you didn't remember this just now, but will you forget it now? No, exactly. Right? They just forget things. Everything's just gone. Woo. Woo. So we spend a lot of time reminding, so much time reminding. Okay. So if we go the first or the second route, we can find hydrogen by taking Kw and dividing by hydroxide. That's 1 times 10 to the negative 14 over hydroxide. We get that one. And then, of course, we would take our pH, the negative log, and we get 11.78. Hopefully, if we do it the other way, POH, take your negative log of hydroxide, negative log of blah, equals blah. pH is equal to pKw minus pH equals 11.78. How nice. Yes? Thymolphthalein at 11.78 would be blue. We will soon learn how to to determine the pH of a weak base solution, but we haven't covered Kb yet, so we won't deal with it on this worksheet, okay? We're gonna do this one and then we're gonna break and then we'll come back. Yes, because this is actually super, super easy. Finding Kb, this is page 29. Finding Kb from Ka of the conjugate acid. Oh, hang on. Did we do weak bases? Oh, I've got my, no, I'm so sorry. I'm on the wrong one. My pages are not in order. 22, page 22. Page 22. Page 22. Strong bases are most often what? We just did this. Can you prove you have big brains? Something that starts with M and then something starts with H. Something hydroxides. Metal, yes. They are most often metal hydroxides. These fit the Arrhenius definition of a base. And what is the Arrhenius definition of a base? They release OH. Whoops, why am I writing two negatives? In solution. Could you give me an example of a metal hydroxide base? NaOH, okay? BaOH2. How many strong Bronsted-Lowry bases are there? There are 2. What are they? We have, is OH a strong Bronsted-Lowry base? Go look. Yeah, O2 minus and NH2. Remember, hydroxide is the strongest base that can exist in water. It isn't itself a strong base. Okay, it's what's produced by a strong base. Yes? Okay. So what are the 2 strong Bronsted-Lowry bases? O2 minus and NH2 minus. Hardly any, so we're not going to bother with them. Not right here and not right now, okay? All the weak bases are Bronsted-Lowry bases. You don't have any weak Arrhenius bases. You might have like a slightly soluble hydroxide, like minimally soluble, but then you would be using a KSP to solve for the hydroxide ion concentration. Does that make sense? Okay. Which means if you are a Bronsted-Lowry base, what is that definition? It is a proton acceptor. So for example, we have ammonia accepts a hydrogen from water and becomes NH4 plus and leaves behind the water has lost a hydrogen, so it becomes OH minus. And because it is a weak base, we have an equilibrium set up. When we were working with weak acids, we could kind of cheat and leave the water out of the equilibrium because all weak acids fit both the Bronsted-Lowry. What's a Bronsted-Lowry acid? It is a proton donor. They fit not only the Bronsted-Lowry proton donor definition, but also the Arrhenius definition of an acid where they simply release hydrogen in water, okay? Weak bases, on the other hand, you cannot leave water out of the equation, because what happens if we take the water out of this equation? What if that's gone? Where does our hydroxide come from? Nowhere. And you cannot be a base if you're not producing hydroxide. So with a weak base, there's no like shorthand method that you have to have the water in there, okay? Otherwise, there's no oxygen for the hydroxide, right? Huh? How do you do that? You can't. Ooh, punctuation trivia. Did you guys know that that is called an interrobang? That is the interrobang. And in fact, the interrobang is actually kind of looks like that. But most people just write it like that because there's no key on the keyboard that looks like that. And it's like the one where you're like, what the heck? I don't know what was with me that day when I was writing this. I think I was like, I'd been writing for a long time. And you know how I get a little weird sometimes when I've been talking for a long time? It's the same thing when I'm writing. So all equilibria involving weak bases must involve water or another Bronsted-Lowry acid as the reactant. Since weak bases form an equilibrium, of course, we can find an equilibrium constant, KEQ. Because this is the equilibrium constant of a base, guess what we call it? KB, huzzah. Could you please write the KB expression for ammonia? Is good? Oh my God, this should not say aqueous. This should say liquid. Water is a liquid, yes. We'll take our break at 1:45. Does that sound good? Okay. Finding patterns, organic chemistry. We have not done a lot of organic chemistry. It is not covered specifically on the AP exam. That's why we are ignoring it, because we have enough to cover. However, one of the key things about science is finding patterns. So let's take a look at all of these weak bases. What do all the names have in common other than ammonia? They all end in, it actually is pronounced "ene," but yes. Okay, it looks like "ein," but it's pronounced "ene." Okay, so we have aniline, hydrazine, ethanolamine, trimethylamine, pyridine, hydroxylamine, dimethylamine. Okay, they all end in "ene." What do a large number of the weak bases, the names of the weak bases, have in common? Not all of them, but a large number. In addition to the "ene," we can go a little further. And we can say they all have, and a large number of them have amine. Yes? What do all the formulas of the weak bases have in common? They all contain which element? Nitrogen. And the nitrogen is attached to what? Hydrogen. So if you have studied any organic chemistry or biochemistry, you may recognize this as a functional group. If you haven't, then you have no idea what that is. A functional group is just one of those things that you recognize. Do you guys, can you think of any other functional groups that we've talked about? The hydroxyl group, okay? OH, where you have C, you know, H3, OH, that is your hydroxyl group. Sorry, what was the other one? The carboxyl group. Okay, so if we have the N with some H's attached, that is called an amine group, which consists of nitrogen attached to other stuff. This is completely beyond the scope of this course, but you may run across it if you're taking biology, for example. Ammonia, obviously, is just ammonia. You can't do anything else with it. Nitrogen generally forms 3 bonds because, of course, it's got 5 valence electrons, which means it's got 3 empty slots, so 3 bonds, yes? And we have hydrogen, hydrogen, hydrogen on ammonia. If you have one group attached to it, that's called a primary amine. I think I've gotten this the right way around. If you have 2 groups attached to it, these would be like carbon groups, the rest of the molecules. So this would be like, you know, CH3 or, you know, CH2, CH3. Did I get it backwards? Biology people, did I get it backwards? Does that sound good? Okay, okay. I thought it was right, but you know, it's been a while. And then we have 3 R groups, which is the rest of that's our carbon chain. And that's called a tertiary amine. Exactly, you do not need to know any of those terms for AP Chem. Okay, I'm just kind of mentioning it now because sometimes it's nice to know things like 1 with a little circle at the top stands for primary. 2 with a little circle at the top, secondary. 3 with a circle at the top, tertiary. Also works for protein folding. Yes? Primary, secondary, tertiary. Yes. Okay. You're like, I've seen this before somewhere. Yeah. So these amine functional groups are found in many organic carbon-based compounds, including, does anyone know what carbon-based compound they are found in? Amines are found in something that starts with A and then another A. Amino acids. Getting a little cross-curricular with biology here. The acid part of an amino acid, what is its functional group? That is a carboxyl group. And that, remember, is our COOH, right? And we know our acids are COOH, which gives us all the carboxylic acids. Okay, this organic terminology is not part of Chem 12, it is not part of AP, and it will not be tested, okay? However, super useful if you're going into any of the biological sciences or if you're doing any organic chemistry along the way. And we are hit 45, so let's be back at 2 after 2. Does that sound good? Yeah? And then we'll work on, you guys can do some review of acid base 1. Hi. Yes. Yes.
I'm just wondering, is that because although we say protein electron material,
Yes.
the property is different,
The property of what?
like each proton and the different substance, or are they like?
They're exactly the same. Yeah. Yeah. You only get different properties when you have like a full element with protons, neutrons, electrons. Yep. Yes. Yeah. So what are we thinking? Are we thinking tests next week, or are we thinking combine the two tests? I think it would give us a lot of extra time. Because today I would just, instead of giving you this, I would give you this over the weekend, right? But we could teach something now. We could do like a whole lesson now. Yeah? I think it's a plan. And nobody else is talking to me, Casey. So you and I, we're on the same page. Let's go, girl. All right. So test is not next week. We're going to have a combined test. Okay, that's going to go sometime. So we're going to learn some stuff. I will give you the acid-base review for the weekend. Okay? On Tuesday? Hey! And it worked out beautifully, didn't it? Yes. Okay. So let's just carry on with KB then. Oh, and Sasha was the lucky winner of the color edition. Yeah. Oh, one of them got printed in color just by mistake. They did it by mistake. All right, page 24. Okay, so the only thing you do with all the amines, it doesn't matter. Here's a whole bunch of reactions of amines with water. Where do you put the hydrogen accepted from the water? So look at all these reactions and tell me, where do you put the hydrogen from the water? Who does it attach to? Where do you put the hydrogen from the water? So we got a hydrogen and it's going over here. To what atom does it attach? To the nitrogen. Okay, so you basically just end up with 5 hydrogens rather than 4 hydrogens. You have the H is attached to the N. Yes? We end up with an extra H attached to the N. So you'll end up basically with a positive ion and a hydroxide. So could you please write the equations for the following reaction of the following amines with water? Yeah, of course. Did you get what I got? Excellent. Yes. Oh, there should be a plus here. Yes. Because of course we're transferring a hydrogen plus on there. Thank you, thank you, thank you. Now, in our continuing story of finding the pH of a solution, the little old lady is back. And when we get to, she's going to her home base. Ha, get it, base? She's going to her home base. So she has shooed away the crows, she's picked up her bag of rice, and she's made it to her home base. But the crows are still happy because they found some kebab on the ground to eat. Look at that, they've got their little kebab, kebab, kebab. So remember, for a weak base, you are going to use a rice table and KB. I know it seems like I'm hammering home a point that should be really obvious, but do you know how many people in a quiz that's called KB quiz, and it says the weak base, blah-de, blah-de, blah, what's its pH, and then they go and write me a Ka expression. I'm like, what the bloody hell, right? Like, I don't even. So I am hoping, but you guys have large brains, so you won't do that, right? If it says base, you're going to use a KB. If it produces hydroxide, you're going to use a KB. If it asks you for a base, oh my God, I had people with bases. It says the weak base, and they're trying to make it produce hydrogen. And I'm like, why? Bases produce hydroxide. Okay, so don't make any of those silly mistakes. I know I'm a little too obsessed with the story, but I do want you to remember that if the little old lady makes it to her home base, the crows need to eat kebab. Okay? So, anytime you are asked for pH or P or H or OH or POH or the color of an indicator, you have to ask yourself two questions. We're going to put a huge star beside this because this is really important. Important. You need to ask yourself, is the solution an acid or a base? And is the acid or base strong or weak? Okay? Just because a question asks you for hydrogen ion concentration, do not assume you are working with an acid. Also, do not assume you are working with a base if it asks for OH minus. Rather, look for clues in the question. So here we have, calculate the hydrogen ion concentration of a 0.1 molar solution of the weak base, aniline. So you're like, oh look, it's a weak base, because it tells me it's a weak base. And it also has a KB. So aniline is going to act as the base, accepting a hydrogen from water, and water acts as the acid. So who are the products of that reaction, of that? We have C6, H5, NH3 plus. And what's our other product? OH minus. What can we fill in our rice table at this point? .1 molar of the aniline, so there's 0.1 molar. What should we do with the water? Nothing, because it's a liquid. I got it right that time. And how about the products? 0 and 0. What shall we do next? Plus x, plus x. And on the other side, we're going to have minus x. 0.1 minus x, x, and x. What would we do now? What would our next tool be? Yes, we can assume x is insignificant. You can do this later on too. It doesn't matter if you do it right here. You can do it later on. It just saves you a little work. Saves you a little writing. And after this, K, B. Do you need to write it? Can you just start plugging in x's? No, you have to write the expression C6, H5, NH3 times OH over C6, H5, NH2. Equals x squared over 0.1, and we don't have to put the minus x there because we have already assumed that it is insignificant. And the KB was given to us in the question. It was 4.3. Whoa, what happened? Oh dear, many things are happening. Okay, try that. 1.3 times 10 to the negative 4.3. It probably is. I got distracted by my page running away on me. 4.3, yes. 4.3 times 10 to the negative 10. And then we just do the algebra, of course. X squared is 4.3 times 10 to the negative 11. You're good? And then we get 6.557 times 10 to the negative 6. And now you have to ask yourself, what does that x value represent? It represents a change in concentration, but remember, we are trying to get close to finding the hydrogen ion. Does x equal the hydrogen ion concentration? It equals the hydroxide ion concentration, yes. So that's equal to the concentration of hydroxide. Please tell me 2 ways to go from hydroxide to pH or hydrogen. Or no, never mind. We just wanted hydrogen, right? So we don't need to do 2 ways. There's only 1 way. So if we want to know hydrogen, how do we do that? Tell your partner, how do you convert from hydroxide to hydrogen? So the expression is Kw is H times OH. You don't need to write that. You can go straight to this here, yes? But that's just to remind you that that is where it came from. Kw is equal to H times OH. But you can go straight to H is equal to Kw over OH, which is equal to, what's the value of Kw? 1.0 times 10 to the negative 14 divided by 6.557 times 10 to the minus 6. Equals 1.52 times 10 to the minus 9. And I think we can only have 2 sig figs, right? Because our KB had only 2 sig figs. So that would then become 1.5 times 10 to the minus 9 molar, and that is our hydrogen ion concentration. See how this was a review of like the, yeah, because the Ka stuff is exactly like the Kb stuff, we just use a Ka instead of a Kb. So, morphine, C17H19NO3 is an addictive painkiller and a weak base, period. It is the principal molecule in the milky juice that exudes from unripe poppy seed capsules. What is the Kb of morphine if 0.150 molar solution has a pH of 10.5? Now, wouldn't it be nice if we could avoid writing C17H19NO3? Wouldn't that be nice? Because nobody wants to write that. Ugh, where do I put the H? Actually, no problem. When in doubt, you can just stick it on the end if you have to. Okay, yes? Opium. Yeah. Now, poppies that you have here are non-opium poppies. Like they've bred them so they don't have the opium. My mother-in-law actually, when she moved to Revelstoke, she had these wonderful poppies that she, got from her mom. She got the seeds and she'd been raising them and blah blah blah. Her husband was like the priest of the Anglican Church, right? And so there she is. She's growing these poppies and she makes poppy seed muffins, and they're lovely and whatever. She gets a visit from the local police constable. Ma'am, did you know that these poppies? And she's like, oh, no, I did not. So anyway, she got rid of them. But she was quite disappointed because they made lovely poppy seed muffins and they were very beautiful. And you probably felt a little good after eating the poppy seed muffins. You get such a small amount of it from that. It's not really going to affect you. But yeah, could be abused, right? So anyway, what we can do is instead, we can just say, let's let the base be B. Okay? Remember we just said the acid is HA. Let's say our base is just B. Okay? So we're going to say B. There's our base. Plus H2O gives us BH plus OH minus. Yes? So this has saved us from so much writing, makes us very, very happy. We are given the initial concentration of the base, and we were given, what were we given? A pH of 10.5. So in order to use that in our equation, we need to, since our unknown is the Kb, we need, and the hydroxide is not our unknown, we should let OH, we should not represent OH with the letter X. Okay, so don't put an X unless it's really actually unknown. We convert the pH. So 2 ways of doing that. POH is equal to pKw minus pH, gives you 3.5, that's our POH. And then hydroxide is 10 to the negative POH, which is 10 to the negative 3.5, which is, there is our hydroxide ion concentration. Is good? Okay, plug that in there. How does the rest of our table go then? Yep, and we just throw that in all the way across, 3.16 times 10 to the negative 4 minus 3.16 times 10 to the negative 4 And probably we might be able to make the assumption that that's insignificant, but why not just leave it just in case? I don't know. You know, it's a bit dodgy there. So I'd say just throw it in. What would you write for your KB expression? Concentration of BH times the concentration of OH minus over the concentration of B equals, and then you just plug in what you've got. So you've got 3.16 times 10 to the minus 4 squared over 1.497. And we get 6.671 times 10 to the negative 7, which would then, let's see, we need how many sig figs? Ooh, that's a good question. How many sig figs? Go back to your question and say, what am I working with here? 1, right? Because our pH only had 1 sig fig, so we can only have 1 sig fig in our answer. Come here. Yes. Did I do it wrong? Okay, hang on. 0.15 minus, I probably punched a button wrong. 3.16 E4 negative equals, I get it should be 0.1497. Sorry, my decimal place is the wrong place. 0.1497, which means this will be 0.1497, which means that should be times 10 to the negative 6. Better? Good. And then to 1 sig fig, that would be 7 times 10 to the negative 6, which means that probably I could have ignored the difference there because I've only got 1 sig fig in the end anyway, but, you know, close enough. A certain weak base has a Kb of 8.40 times 10 to the negative 7. What concentration of this base will produce a pH of 10.16? When they say what concentration of this base, that's always going to mean what is the initial concentration of the base that will give us that pH. We don't know the formula of the base. What should we write? I would just write something like let B represent the base. Just so that you've defined your terms, right? Our initial concentration is our unknown. As always, the initial concentrations of the ionized stuff is 0 and 0. We are given a pH, which means that we need to convert that into POH and then H+. Okay. And so we've got POH is equal to 14 minus 10.61 is 3.84. OH is 10 to the negative QH, which is 1.445 times 10 to the minus 4. Throw everything in. Oh, we didn't throw everything in. You guys get to do that. You want to throw everything in and solve it? I'm recording the rest of it, so yeah. Did I do it right? Yeah? Always so exciting. I was always like the 92 to 94% student because I could never get everything all right. Just kind of things go, well, you know from my answer key, everything's here, it's there. Yes. Oh yeah, there's a 0 there. See? Yeah, 0.025. Yeah. There we go, that's better. So is this like all super familiar? Like it's all looking exactly like the KA stuff? Yes? Okay. So we have some exercises here. But we're not going to do the exercises. We're going to go to 5.2b. Are your brains up for it? Can you do it? Should we go and walk around the hallway 3 times? Okay, we're going to go walk around the hallway. We're going to actually, you know what? We're going to go outside. And you guys are going to go run around the parking lot and come back. Come on, let's go. Okay, now I need to get my breath back because I'm horribly out of shape. Okay, not all weak bases are amines. Some other common substances that act as weak bases, this is page 29, are some of the anions. Now, I'm going to start with the ones that do not act as weak bases, okay? These are the substances which do not act as weak bases. What have I done with my pen? There it is, good. ClO4, I minus, Br minus, Cl minus, NO3 minus, and HSO4. Does this list look familiar? What do all these anions have in common? They are the conjugate bases of strong acids. So they cannot act as bases. Everything else can act as a base, okay? They can all accept protons, other than those. Oh, I guess I left a space for that, strong acids. So remember, the stronger the acid, the weaker its conjugate base. Therefore, the conjugate bases of strong acids are so weak, they are unable to accept protons and act as bases. So other than the two strong bases, what were the two strong bases? O2 minus and NH2 minus in the gray section at the bottom of the table, and the conjugate bases of the strong acids. All of the rest of the anions in the table are weak bases. So everything in the white section, all the way from IO3 minus all the way down to OH minus. You will not be given the Kb for these anions. It is because it is a simple calculation to find the Kb of the anion. Kb is equal to Kw divided by Ka of the conjugate acid. I forget, did I prove this on the next page or did I just like go on with it? Oh yeah, so where did this formula come from? Do you care where this formula came from? I don't know. We'll go through it really quickly, okay? So let's say we have an acid, HA. It dissociates into H plus and A minus, so those go on the top. HA goes on the bottom. For our conjugate base, here's our conjugate base, we produce HA and OH minus, HA and OH minus, and the base goes on the bottom. Thank you, Casey. Now, if we multiply these two Ks together, right, we have our Ka, we have H plus times A minus over HA. So we have A minus over HA, that's right here, yes. And we have HA over A minus in our Kb, yes. And guess what? What do those do? They cancel out. So what we're left with then is Ka times Kb is equal to, the only things left are hydrogen times hydroxide. And what is hydrogen times hydroxide? That's Kw. So we've got H times hydroxide is equal to Kw, and we've got that's equal to Ka times Kb. So now we have Ka times Kb equals Kw. Okay, you are not going to have to derive that. I can't remember if that's given to you on the data sheet. It might be on the AP data sheet, but it's simple enough to remember anyway, so I don't think it should, really trouble you much. This formula works not only for anions, but also for molecular or uncharged bases like ammonia. So Kb of ammonia is equal to Kw over Ka of the conjugate acid. Who is the conjugate acid in this case? Who is the conjugate acid of NH3? I want the conjugate acid. NH4 plus. So you could go look up the Ka for NH4 on your data booklet, right? You could be like, where is NH4? Ammonium ion, there it is, NH4. Its Ka is 5.6 times 10 to the negative 10. Okay, 5.6 times 10 to the negative 10. I'm gonna write that one down first because I might forget it. And our value of Kw is 1.0 times 10 to the minus 14. And we get 1.8 times 10 to the minus 5. Using the formula, calculate the Kb for F minus. First, let's prove that F minus can act as a base. Can it act as a base? What would it form? HF plus OH minus. And we have to ask ourselves, is this a weak acid or is it a strong acid? It is weak, and therefore, yes, F minus can act as a base. If it were strong, we would have to say, oh, no, that reaction simply will not happen. So since the conjugate acid is weak, F minus is able to act as a base. So what would we write as our formula? Kw over Ka, and we're going to abbreviate this shortly, but for now we're going to write of the conjugate acid. Who is the conjugate acid in this case? HF. So Kb is equal to Kw 1.0 times 10 to the negative 14 divided by the Ka of HF, which is 3.5 times 10 to the negative 4. And we get 2.9 times 10 to the negative 11. Now, if you were going to then do something with this, other than just like have that be your answer, I would say you would keep, 2.857 times 10 to the negative 11 and round at the very end. Do not round early. Yes? Otherwise, you end up with rounding error. So if you were to use 2.9 in, like, say, a rice table situation, you would probably end up with a rounding error, especially because that's a 5. That's like close to halfway, right? So you would probably be too high, okay? It may be always a pain in the butt to write Kb of whatever is equal to Kw over Ka of the conjugate acid, whatever, rather than just Kb equals Kw over Ka. But it is to prevent you from making this most common mistake. Let's find the Kb for HCO3. Here's how to do it wrong. Kb of each CO3 is equal to Kw over Ka. Kw is 1 times 10 to the negative 14. Ka of HCO3, 10 battery is low, I know, just give me 10 minutes, is equal to 5.6 times 10 to the negative 11. Yes? And we toss that in there. What is wrong with how I've done this? Yes? That is the Ka of HCO3. We need to use the Ka of H2CO3. Now, do you have to write out this whole thing every time? I would say probably not, as long as you can remember you're going to write Kb of whatever the base is equals Kw over come here. Let's call it B minus. Kw over Ka of Hb. Yes? So you're going to stick an extra H on there. I would make sure that I write that in every time because that way I won't forget. Okay, and use the wrong one if I've got an amphiprotic substance. But for starters, you can always be like Ka of the conjugate acid if you want to remind yourself. It's just up to you what makes sure you don't make that mistake. Now let's do it correctly. Here is carbonic acid. Okay, so we have Kb of HCO3 minus is equal to Kw over Ka of H2CO3 equals 1 times 10 to the negative 14 over 4.3 times 10 to the negative 7 equals 2.3 times 10 to the negative 8. Oakley dokley? Is straightforward. You just have to remember it, right? All right, here's another one. Calculate the Kb for Br minus. Do you remember what I said the first step was? The first step is see if Br minus can act as a base. What would we get if it acts as a base? HBr plus OH minus. What have we made here? We have made a strong acid, and therefore, no. Okay, you cannot form a strong acid. It will not go that way. Okay? So Br minus does not have a Kb. There's some exercises. We've learned a crap ton today, haven't we? Yeah. So, what shall I assign you? I don't know. Okay. Give me like 3 minutes to organize what you should be doing for yourselves. Or do you just want to get this? Do you want to get the review and start on that? Get the review. Start on the review. Yeah, do that. Or you got an extra one for her? Okay.
you might just combine two tests together.
We are combining the two.
Oh,
We are combining the two, yes. It's a short one. It's like it's not a huge unit. Do you know what I mean? That's why combining it is not the worst thing in the world. It's not like 100 million questions. Yeah, I know, I know. And I don't always expect you to do all of them. They're just kind of there for, the people who need that comfort of having done a million questions before they write the test. Yeah. I hear you. I would probably do them all too. I'd probably just be like, okay, fine, I'm going to do them all.